Okay, have you ever seen a magic trick so good it literally makes you question everything you know about the physical world? Because what you're looking at right here, it is definitely not camera trickery. That's a magnetic cube just levitating in midair, locked in perfect, effortless balance above a tiny, chilled disk. Honestly, it looks like magic, but it's actually one of nature's most mind-bending quantum phenomena. We are literally staring at a material that has unlocked the secret to perfect, frictionless energy.
And that brings us to a massive global problem, and honestly, an incredible question. How can electricity flow forever without losing a single drop of energy? You see, at normal temperatures, every single material out there, even the copper wires in your walls, has electrical resistance. It's kind of like a narrow pipe resisting the flow of water. And because of that resistance, we constantly lose massive amounts of energy as heat in our power grids and everyday devices. But what if we could just eliminate that resistance completely? What if energy could just flow infinitely?
Welcome, everyone. In this explainer, we're going to demystify one of the absolutely most intriguing and revolutionary concepts in modern solid-state physics, the quantum mystery of superconductivity. We're going to break down how this works, why it totally breaks the rules of classical physics, and how it's quietly powering the future of our technology. Okay, let's dive into our roadmap for today. We'll cover 1. The superconductivity mystery. 2. Zero resistance and levitation. 3. Soft versus hard superconductors. 4. Solving the quantum puzzle. 5. The high-temperature revolution. And finally, 6. Powering the future.
All right, starting us off with Section 1, the superconductivity mystery, a century-old scientific puzzle.
To really appreciate where we're going with this, we kind of have to look at where it all started, right? Because this phenomenon completely shocked the scientific establishment. Way back in 1911, Dutch physicist Heike Kamerlingh Onnes was playing around with liquid helium. He cooled mercury down to near absolute zero, and suddenly its electrical resistance didn't just slowly taper off, it vanished entirely, just dropped to absolute zero. Now, take a look at the massive 50-year gap on this timeline between 1911 and 1957. The scientific community knew this was happening, for sure, but the why and the how remained a complete mystery for nearly 5 decades, until the BCS theory finally came along.
So the real key to Onnes's discovery is something called the critical temperature, or TC. This is basically the exact threshold temperature where a material's direct current electrical resistance suddenly vanishes completely. For Onnes's mercury, that threshold was a freezing 4.2 Kelvin. To put that into perspective, that's about negative 452 degrees Fahrenheit. But once you drop below that line, current can flow indefinitely. We are literally talking about years of persistent electrical current without any measurable decay. Crazy, right? Moving right along to Section 2, Zero Resistance and Levitation, breaking the rules of classical physics.
You know, when materials cross that critical temperature threshold, they start breaking the rules of classical physics in some pretty spectacular ways. And just to give you an idea of how monumentally important this rule-breaking behavior is to science, just consider this number, 5. Yep, there have been 5 separate Nobel Prizes in physics awarded for research in superconductivity between 1913 and 2003. So this isn't just some niche quirk of nature, it is a fundamental unlocking of quantum mechanics. And one of those Nobel-worthy discoveries is actually the exact thing that caused that levitating cube we saw earlier. It's called the Meissner effect. Discovered in 1933, scientists realized that when a material transitions into its superconducting state, it literally expels magnetic fields from its interior. The scientific term is perfect diamagnetism, and this is really what distinguishes a true superconductor from something that's just a perfect conductor. It actively pushes the magnetic lines of force out, creating this invisible magnetic cushion that lets objects levitate in perfect lockstep. It is so cool.
Let's move to Section 3, Soft versus Hard Superconductors, classifying the quantum materials.
Now, it turns out not all of these incredible materials behave the exact same way when you expose them to magnetic fields. We actually see a pretty sharp contrast between 2 main categories here. Type I, or soft superconductors, are your pure metals like lead and mercury. They completely expel magnetic fields, but the catch is they have a very low tolerance. If the magnetic field gets too strong, boom, they lose their superconductivity entirely. But type 2, the hard superconductors, these are the real game changers. We're talking alloys and complex materials like niobium titanium. Instead of completely pushing out a strong magnetic field, they let it partially penetrate through these quantized flux lines called vortices. What that means is they can sustain incredibly high magnetic fields without losing that precious superconducting state. And as you'll see in a minute, this type 2 property is exactly what makes things like modern MRI machines possible.
Next up, Section 4, Solving the Quantum Puzzle, the brilliant 1957 BCS theory. Okay, so we know how they behave, but how do they actually work on the inside? Remember that 50-year gap we talked about? Well, it was finally closed in 1957 by three brilliant physicists, Bardeen, Cooper, and Schrieffer, giving us the famous BCS theory. Now, we all know from basic science that electrons have a negative charge, and normally, negative charges completely repel each other. But below the critical temperature, the BCS theory proposes something wild. These normally repelling electrons actually team up. They form bound states called Cooper pairs. It's kind of like they become microscopic dance partners, coordinating their movements so perfectly that they can just glide through the material's atomic lattice without bumping into anything at all. Let's actually break down the mechanics of this dance step by step. First, as a moving electron flies through the lattice, its negative charge attracts the positively charged atoms around it, slightly distorting the lattice inward. Second, this physical distortion creates a tiny ripple, an atomic vibration that we call a phonon. Third, a second electron comes along and absorbs that phonon, effectively getting pulled right into the wake of the first electron. So through this exchange of virtual phonons, these bound Cooper pairs condense into a macroscopic quantum state. And because their motion is perfectly correlated with the rhythm of the atomic vibrations, they move smoothly without any friction whatsoever. No collisions literally means no energy lost as heat. Which brings us to Section 5, the high-temperature revolution, the 1986 plot twist. The BCS theory was a huge triumph. It neatly explained everything, until the universe decided to throw a massive curveball. For decades, the theory dictated a strict speed limit, predicting that this phonon-mediated superconductivity simply could not happen above roughly 30 Kelvin. Period. But then, in 1986, scientists Bednorf and Mueller discovered a complex copper oxide material, a cuprate, that became superconducting at 35 Kelvin, and the idea spread like wildfire. Very quickly, other researchers found cuprates working at 92 Kelvin and eventually way up to 134 Kelvin. This completely shattered those old theoretical limits. And honestly, the most exciting part? To this day, the microscopic theory that describes conventional metals doesn't fully apply here. Science literally still does not completely understand exactly how these high-temperature superconductors work. Now, I should clarify, when a physicist says high temperature, they mean something very different from you and me. We are still talking about absolutely freezing conditions. But look at the difference here. The old materials required liquid helium, which cools things down to negative 452 degrees Fahrenheit. Liquid helium is incredibly expensive and super tricky to handle. But these new cuprate materials, they crossed a magic threshold, 77 Kelvin, or negative 321 degrees Fahrenheit. Why does that matter? Because that is the boiling point of liquid nitrogen, and liquid nitrogen is cheap, it's abundant, and it's easy to use. This single breakthrough dramatically reduced cooling costs and dragged superconductors right out of the theoretical lab and into practical reality. And finally, Section 6, Powering the Future, bringing quantum oddities into the real world. So how is this quantum oddity actually being used to shape the modern world we live in right now? Well, the crucial point here is that those type 2 hard superconductors we talked about earlier, the ones that can handle huge magnetic fields, they are totally revolutionizing technology. Because superconducting wire has zero resistance, it can handle massive electrical currents without melting. When you coil that wire, you create incredibly powerful electromagnets. And these are the exact magnets used in MRI machines in hospitals worldwide, and even in giant particle accelerators. Remember that Meissner levitation effect? Well, that is the basis for those frictionless maglev trains that literally float above the tracks. We're looking at the very real future of lossless power grids where absolutely zero energy is wasted. And these materials even serve as the foundational qubits for next-generation quantum computers. We've definitely come a long way from a bizarre observation in liquid mercury to the absolute cutting edge of modern technology. But the ultimate prize is still out there. Thousands of brilliant minds are currently hunting for a material that exhibits these exact properties without needing any extreme cooling at all. So I want to leave you with this provocative thought. What happens to our technological world when we finally crack the mystery of room temperature superconductivity? When infinite, frictionless power can just sit right there on your desktop? The quantum revolution is really just getting started, and I, for one, absolutely cannot wait to see what we discover next.